We will learn basic number theory. Number theory is a huge area in mathematics, so we cannot really learn many things. We will learn very simple and basic things here. So the first section is about divisors. Yeah. So let me begin with the definition. So we have two integers, n and d. These are integers. And we assume that d is not 0. And we say that d divides n if n is dk for some k, integer k. So this is the definition. D divides n if there is an integer k such that n equals d times k. This is, and there are several ways to say this. So d divides n, they all mean the same thing. D divides n. We also say that n is divisible by d. And also we say that d is a divisor of n, and also we say that n is a multiple of d, and also say that this is notation, d vertical bar, and this means d divides n. They all mean the same thing, and the definition is this. Okay. So example, 7 divides 84. So we write like this. You can write this. This means 7 divides 84. Because 84 is 7 times something, integer something, 12. And 3 divides minus 6. Because minus 6 can be written as 3 times minus 2. Minus 2 is an integer, so it satisfies this condition, so this is okay. 4 divides 0. Does 4 divide 0? Yes, because 0 is equal to 4 times an integer, 0. Alright? Now let me ask you a question. In the next page. So you need to remember this definition. You have to remember this all the time. Yeah, it's very basic, and probably you already know this. Now let me ask you a question. Does 0 divide 1? Do you think 1 divides 0 divides 1? Okay, what about this then? Another question. Divide 0. The answer to both questions is no. No, no. Because? Why? Here 0 equals 0 times something, anything. So why don't we say 0 divides 0? Does this satisfy the definition in this case? This is not true. Obviously, 1 cannot be written as anything. Anything for any number x is going to be 0. So it's never going to be true. But here it seems like 0 is 0 times 0, or 0 times 1, anything. Seems to satisfy the condition. Do you think this is true? I mean, this sentence is true? It does satisfy this, but it does not satisfy this condition. We always assume this. D divides something that we always assume that D is not 0. So if this is 0, we'll never say 0 divides something. So we will always divide by some number, not non-zero number. All right? So both are 0. Both are no. No, no. Because we never divide by 0. And we have simple theorem. If D divides N and D divides M, then strange. D divides their sum. Okay? And second, if D divides N and M, D divides their difference. And if D divides M, D divides C times M for any integer C. All right? Yeah, it's quite obvious, but let's prove this. Let's prove the first one. So to prove this, so with these two are the assumption. So from this, what can you say? N is equal to D times A, right? Because D divides N. By definition, we can find integer A, and M is equal to D times B, where A and B are integers, right? This is equivalent to saying this. We have some integers for some A and B. Now, what is N plus M? Now, because dA plus dB is, you can factor D. And A plus B is also an integer, so we express N plus M as a product of D and an integer. So this means that D divides N plus M. You can prove a statement like this. The second one is similar, third one, they are all similar. 2 and 3 are similar. You can prove this similarly. Okay, so divisors are like this. And this is, the next definition is very well known and very important. Simple but very important. An integer greater than 1 is called prime if 1 and itself are the only divisors. So it's called prime. And if it's not, it's called composite. An integer greater than 1 is called composite if it is not prime. So probably you already know this. The 7 is prime, right? There are only 2 divisors of 7, 1 and 7. You cannot find anything else. Yeah, I should say positive divisors, because -1 is also a divisor. Yeah, we only consider positive divisors, and if 1 and n are the only divisors of n, then n is called prime, like 7. And 39 is not prime, so it's composite. Because 39 has another divisor, 3. 3 divides 39. 3 is not 1, 3 is not 39, so. What about -1? This is neither prime nor composite, because we only consider integers greater than 1. So integers greater than 1 is always a prime or a composite. But integers less than or equal to 1, we don't consider that as prime or composite. So -1 is neither, like -7, neither prime nor composite, like that. Okay, is this clear? Okay. So prime numbers are very important, and many mathematicians have been studied. Have studied prime numbers, but still we don't understand completely. We only understand very little of prime. Okay. So prime numbers are considered to be like base elements of integers, because we will see that every integer can be written as a product of prime. So some people say that primes are like atoms of integers. So they are important. So how can we determine whether a given integer is a prime or not? How can we determine whether given integer n is prime? So for instance, like 39, we know that's not prime. But what if the number is very big? So if n is not divisible by let's write the other way. So we already know this from the definition. N is prime if and only if what? Of course, and we assume that n is greater than 1. N is not divisible by 2, 3, up to n minus 1. If n is not divisible by this, then we can say that it is prime. And it is if and only if condition. 7 is not divisible by 2, 3, 4, 5, 6, so it's a prime. This is just definition. But this is not very good because there are many things to check. If n equals 7, there are not many numbers. But what if n is very big, like 2017? In this way, we have to check like 2015 numbers. We have to check 2, whether this is this divisible by 2, is this divisible by 3, 4, 5, up to 2016. So you have to divide this by many times, divided by some number many times. So it's not very efficient. But there is a much better way to do this. So theorem, again, n is assumed to be greater than 1. N is composite. So in other words here, n is composite if it is divisible by one of these, right? Because if prime means not composite, composite means not prime. If and only if n is divisible by, say, by d for some d between 2 and square root of n. So you don't have to look at n integers up to n minus 1, but you only need to look at square root of n, which is much smaller than n minus 1. Like, if n equals 100, square root of n is just 10. So it's much smaller than n. Proof is quite simple. We have to prove two things because it's if and only if condition. This says P, if and only if Q, so you have to prove two things. If P, then Q. If Q, then P. But one of them is very simple, like this way. If this is the case, n is composite, right? This is just obvious. Do you see it's obvious? Because we already found a divisor, not 1 and n. This is still less than n, right? This is square root of n is less than n if n is bigger than 1. So we already found we already found D between 2 and n minus 1, so it is a divisor, so it's not a prime, or it is composite. This one is obvious. So this part is the thing that we have to prove. If this is composite, by definition, it has a divisor between 2 and n minus 1, but not it. In the definition, it doesn't say that it must have divisor here. We have to prove this. Since n is composite, what can we say? N equals a times b for some ab great not 1 and n, so between 1 and n. Okay? Otherwise, it will be a prime. Now, let's say we have two cases, either a greater than or equal to b or b greater than or equal to a. Assume, what if a is greater than or equal to b? Then what? B squared less than or equal to a times b. Okay? Because b, this is b times b, a times b, a is greater than or equal to b, so we have this. This is n. So from here, b is less than or equal to square root of n. In this case, we have found the divisor of n less than or equal to n. More precisely, we can say we already know that p is greater than or equal to 2. We found such d. This is okay. The other case is similar. We just consider a squared instead. A squared less than or equal to n. So we just found integer between 2 and square root of n, which is a divisor of n. So this is what this is saying. So this is the proof. Any question? So let's try to see if this is prime. Do you think it's prime? 2017? We can use this theorem. Example. Square root is 2017 prime. Before, by using definition, we had to check 2015, which is a big number. We cannot really do that today. But what is square root of 2017? This is 44 something. So we only need to check uh, 2, 3, 4, 44. One of divides 2017. If none of them divide, then we can conclude that this is a prime number. Otherwise, we can find a divisor, so it's not going to be a prime. But in fact, these are 43 numbers, which is much less than 2015, but still quite many for us. But we only need to look at prime numbers here, because if this has prime, we will prove this later, but we don't really need all of them. We only need to check prime numbers. Because if something that's not a prime divides this, there will be a prime smaller than that one divides this. So like 11, but 43, I think, is the last prime number, less than 44. And you can check that this is not divisible by 2017 is not divisible by any of this. So it's a prime. So this year is a prime year. question? Yeah, if you have time, try to divide this by these numbers. And you will see that they're not divisible. And that's the theorem. The previous theorem says that these are enough to check. You don't have to check like 47 or 51, which is not a prime. 53, or you don't have to check. Okay. Right. Let me write an algorithm testing whether an integer is prime. Integer is prime. So input n, integer. It will be an integer greater than 1. Output is going to be either true or false. So here is the algorithm. This is the name, is underscore prime n. So this is just the name of the algorithm. This n means it's the input. Now we have this thing. So we can use the previous theorem. We only need to check whether n is divisible by integer d between 2 and square root of n. So for d from 2 to square root of n, but we want this to be an integer, so we put this square root of n floor. Okay? If d divides n, so this means d divides n. Return, what does this mean? If this is true, that means d is a divisor. We have found the divisor. We can immediately say that it's not a prime. So we can return false. Return false. Otherwise, it will repeat. So after finishing this for statement, we're going to return. So what does this mean? If this does not return false for every d, that means it's not divisible by d. So if the for statement is finished, that means it's going to be a prime. So we return true. So this is an algorithm that tests whether given integer is prime or not. Any question about this? Okay, now I'm gonna tell you this theorem called fundamental theorem of arithmetic. 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 Okay. Any integer greater than 1 can be written uniquely as a product of primes. Like this, n equals p P1, E1, PK, EK, where P1, they are distinct primes in this increasing order, the primes, distinct primes. EIs are like positive integers. Okay? It means that every integer has a prime factorization like this. You can always factor integer greater than 1 into primes. So for instance, 24 can be written in this way. This is 8 times 3, so 2 cubed times 3 raised to 1, which is what? Just 3. And this is unique. You cannot find a different way. And 60, this is 2 squared 3 times 5, like that. You can always write the prime integer greater than 1 like this. What about 7? Just 7. We have just one thing. This is already a prime factorization because everything is prime. Okay? And we just checked 2017 is 2017 raised to 1 because it's a prime. Yeah, this is a very useful theorem, and we already know this. Any question about this? And we're not going to prove this, by the way. Now here is another famous theorem. There are infinitely many primes. There is no maximum about prime. No matter how large prime you found, there will be a prime bigger than that. Infinite limit, because infinite limit. Like integer. Integer has no bound. Prime numbers, they also don't have any bound. You can find arbitrarily large prime number. Infinitely many. Okay, let's prove this. Proof is very interesting. So one of the well-known indirect proof using contradiction. So suppose that we have finitely many prime numbers. Suppose that this is not the case. Suppose that there are only finite primes. And we will find a contradiction, but after doing something, if we reach a contradiction, that means this assumption is false. That means this is true. Okay? This is a proof technique that we learned. Indirect proof. Proof by contradiction. Okay, so because we are assuming that there are only finitely many primes, let's list them all. Let P1, P2, Pn be the list of all primes. There is no other prime because we assume that there are only finite. We just list them all. Now we are going to consider let capital N be the product of all of these plus 1. Okay? So this is not divisible by any of this. Then N is not divisible by any of this. Right? Because if you divide this by P1, the remainder is 1, so it's not divisible by P1. Same for P2, P3, etc. up to Pn. Not divisible by any of this. But the theorem, fundamental theorem of arithmetic says that this must have a prime factorization. It must be divisible by some prime. Otherwise, it will be the prime. It will be a prime. That means n is a prime number. Right? Otherwise, it must be divisible by one of the prime, which is just here. But what is this? This is none of this, right? This is bigger than all of this. We said that we only had n primes, but we found a new one. This is a contradiction. This is not equal to P1, Pn, of course. This is a contradiction. To the assumption that P1 dot 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 Pn are all the primes. That means this assumption, there are only finitely many primes, is not true. So there are infinite many primes as stated. This is the proof. Very simple, right? This just you only need to consider this. It's a very nice, simple proof. Yeah, if there were only finitely many primes, it would be quite easy to study number theory. But there are infinitely many, so number theory is difficult. Any question, by the way? So let me give you an example that we don't really know. I mean, not just us, but all people. We don't really understand the prime very well. Twin primes are a pair of primes differ by 2, like p comma p plus 2. P and p plus 1, both primes, they are called twin primes. For instance, 3 comma 5. They differ by 2. They are both prime. 5 comma 7, right? And 11 comma 13, 17 comma 19, like that. You can find things like that. Do you think there are infinitely many twin primes? This is unknown. We don't know. So it is conjectured that there are infinitely many twin primes, but no one was able to solve this so far. There are infinitely many twin primes. Very old conjecture, like maybe more than 2,000 years old. It's a very old, very difficult problem. No one has solved this. But recently, there has been some progress on this. What does this mean? Twin prime means two prime numbers which are quite close each other, right? Just differ by 2. So people try to generalize this concept, like two, let's say prime numbers differ by like 10, right? Or 12 or 100. So let's say k, so this is not a common notation, but let me simply say k twin prime. Define k twin primes are the pair like p comma q both prime, and their difference is less than k, less than or equal to k, right? We fix k, so 2 twin prime is exactly just twin prime, right? So we, instead of looking at prime numbers differ by 2, we can make this larger. And like several years ago, not like 2013, something like that, a mathematician proved that there are infinitely many k twin primes for k equals 70 million. There's a huge number, of course, but finite, still finite. Compared to infinite, 70 million is only a small number. So I forgot his name, but he's a Chinese, originally from China. But he's, interesting thing is that this guy, he's a professional mathematician, of course. He has PhD, but he was kind of not very active in research. But he published it, published his paper. I think when he published this, he was almost 60, a little less than 60, but 50 something. Yeah, kind of not young for mathematicians, but he didn't publish many things before that. So people didn't, at the first time, people were kind of suspicious about this because it's a very big result. But it turns out that his result was correct, and he became very famous, and he came to many conferences to give a talk. Actually, in 2014, in ICM, International Congress for Mathematicians, it is the most famous conference or congress in mathematics. It holds every 4 years, and if you have heard of Fields Medal, this is the meeting where Fields medalists are determined. But anyway, it was held in Seoul, Korea, 3 years ago, and he was invited there, and they gave a talk there. But anyway, he proved after this, people were trying to solve these problems, the twin prime conjecture, and they decreased this number. Like, it was not optimal in his proof, so people tried to decrease this number gradually, and I think people were able to prove that there are infinitely many two twin primes for 200 something. I don't know exact number, 200 something. Let's say 200. So they decreased this number very dramatically. So we still have to go. There are more ways to go. We want to decrease this by 2. If you can show that it is true for k equals 2, then twin primes conjecture will be proved. And there will be a very big progress in mathematics, in number theory. But anyway, this is a very simple conjecture. I mean, the statement is very simple. Everyone can understand very easily. But the proof is very difficult. No one proved this so far. But there has been some progress like this. Right now, let's talk about GCD. We have two integers, m and n. Integers not both 0. One of them can be 0, but not both 0. The greatest common divisor of m and n is the largest integer that divides both m and n. An integer that divides both n and m and n is called a common divisor. And greatest common divisor is the largest one among them. Largest common divisor, greatest common divisor. And we usually denote this by GCD of m, n. Greatest common divisor of m and n. So for example, GCD of 30, 24 is 6 because divisors, we only need to consider positive divisors because we are considering greatest anyway. So positive divisors. Let's list all the divisors of 30. So 1, 2, 3, 5, 6, 10, 15, 30. These are the positive divisors of 30. Positive divisors of 30. Of 24. 1, 2, 3, 4, 6, 8, 12, 24. So the common what are the common divisors? Common divisors are 1, 2, 3, 6. So these are the common divisors. 1, 2, 3, 6. And the greatest common divisor is, of course, 6. GCD is 6. You consider all common divisors, and the largest one is the greatest common divisor. But of course, this is not the best way to find the GCD. We will learn how to find the GCD efficiently. Okay, so there is a theorem. If you have a prime factorization, GCD is very easy. The theorem. M, n greater than 1. And we have prime factorization. M equals P1, A1, P2, A2, PK, AK. And n, P1, B1, P2, B2. Yeah, when I state the prime, the fundamental theorem of arithmetic, I assume that they are all positive. But now we're going to say that they are non-negative. They can be 0. That means A1, 0 means we don't have P1 factor there. Okay? Because we want to say that they have the same set of primes here. But we can assume this because this can be 0. If they don't have any common prime, it will be 0. If, for instance, m has prime factor 2, but n does not, then this is positive, this is going to be 0. So, yeah, we will have all possible situations here. These are distinct primes. P, yeah, we can say that these are distinct, so we can list them in decreasing order. Distinct primes. Then the GCD of m and n is P1 to, you can just take the largest among them. Maximum of, minimum of A1, B1, P2 to minimum of A2, B2, PK to minimum of AK, BK. Okay? So once you have prime factorization like this, GCD is very easy. So example, 30, we have this prime factorization. And 24, we know that, right? But we want to have the same set of prime. So 5 is missing, so we can just add 5 to the 0. Okay? So that we have the same list of prime. Then what is the GCD? 24. So for 2, you take the minimum of 1 and 3. 1 is smaller, so it's 1. 1, minimum of 1, 1, just 1. Minimum of 1 and 0, 0. So it is 2 times 3 is 6. So we already found 6, but now we can check using this theorem. Okay, so GCD is like this. So once you learn GCD, it's time to learn LCM. So definition again, n. Now we will assume that they are positive integers. Then the least common multiple of n and m is the smallest positive integer. Positive integer that divides that is divisible by both m and n. This is a common multiple. Divisible by m means it's a multiple of m. Divisible by n means it's a multiple of n. So it's a common divisor, a common multiple. We find the smallest one, so it's the least common multiple. So the name actually says everything. And we denote this by LCM, MN. So for example, let's compute LCM of 30 and 24. So multiple of 30, multiples of 24. Let's list them all. So 30, 60, 90, 120, 150, 180, etc. These are the multiples, positive multiples of 30. Positive multiple of 24, 24, 48, 72, 96, 120, and etc. Now, what is the smallest common multiple, least common multiple? 120 appears here and also here. This is first time that appears. So this is the smallest common multiple. So it's the least common multiple, so 120. Okay? And we have a similar theorem as before. For multiple LCM, if we have prime factorization, m and both greater than 1, m equals p1, a1, dot, 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 pk, ak. We are assuming the same situation. And what is LCM? Now, instead of taking the minimum, now we have to take the maximum. P1 and max A1, B1, dot, 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 PK, max, AK, BK. So in this example, 30 is 2 times 3 times 5, is 1, 1, 1. 24, 2 to the 3, 3 to the first, 5 to the 0. So the LCM, you take the maximum of 1 and 3, which is 3. Maximum of 1 and 1. Maximum of 1 and 0. So this is 120 as we computed over here. So if you have a prime factorization for both, then the LCM and GCD, they are very easy. Any question? All right. Now, there is an interesting theorem. M times N is equal to LCM. So product of two numbers, integers, positive integers, they are both positive, is equal to the product of LCM and GCD. We always have this. Why? Proof. We assume the same thing. P1, A1, PK, AK, P1, B1, PK, BK. What is LCM? We take the maximum of this. Max A1 plus B1 dot 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 PK max AK plus BK. Okay. And GCD, we take the minimum. Mean. AK, BK. So what is the product of them? LCM times GCD is, I'm just writing the same thing, just add the two exponents. Oh, you should have told me something, right? This is not, this comma, it must be comma, right? A1, comma, 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 not plus. A1, comma, B1, plus, we add these two together. Dot, 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 and PK, mean, max, let's write max first. AK, BK, right? Now, what is this, by the way? Max x comma y plus mean x comma y. You have two numbers, x and y. You add the larger one and the smaller one. Then you will add both. This is always x plus y. Okay? Because you add the bigger one and then smaller one. If they are the same, they will be always the same. Otherwise, you add one. If x is large, you add x plus y, or otherwise you add y plus x. They are the same. That's it. So this is, because of this part over here is equal to P1, A1 plus B1, PK, AK plus BK. But this is M times N. Okay? That's the proof. So LCM times GCD is always M times N.